All right, so section 5.4. We're going to talk about sum and difference formulas. So we've done some homework problems over the course of. We did some in chapter 4. We've done some in this chapter where we saw, and I'm going to write this in red just to make it more stand out a little more. That, for example, the sine of u plus v does not equal. We can't just separate the two. Doesn't equal sine u plus sine v. So we can't distribute the sine. Nothing like that. Unfortunately, it's not quite that easy. And we've done some homework problems where we saw that when we add two angles together, it's not the same as taking the sine of each one of them individually and then adding those together. And that's true for cosine and tangent as well. Unfortunately, it's not quite that nice. So what we're going to do today is write down the formulas for what happens when we are adding two angles together. And the reason that we're going to do that is sometimes we can separate things so that our angles are the angles that we're adding together are nice unit circle angles, so we can get exact values for those. And the other reason is sometimes it's beneficial to separate things out in terms of the different sines and cosines of the different angles, and then the equations that you work with, sometimes some things cancel, and then it makes them nicer to work with. So a couple of reasons that we do this. So our formulas that are correct. Sine of u plus v equals sine u cosine v plus cosine u sine v. And then let me make I try to put a little tail on my v's and a little down thing on my u's so they look different. And before I write the next one, these all come from coming up with these it's a good amount of work, but it all comes from right triangle trigonometry that we've used before, using the x coordinates and the y coordinates of the various triangles that are involved in these things to come up with the formulas. All right, so sine of u minus v is sine u cosine v minus cosine u sine v. So a couple of things to help you. The more familiar you are with the equations, the easier they are to work with. So a couple of things with the sum and difference formulas. The sum formula, the difference formula. Notice we have the sine and cosines mixed together, but the signs, the plus and minuses, agree. All right, so cosine u plus v equals cosine u cosine v minus sine u sine v. So for this one, the cosines are together, the signs are together, but the plus minus sign is opposite. And cosine of u minus v, cosine u cosine v plus sine u sine v. So those are our sum and difference formulas for sines and cosines. And the sum and difference, yes?
So why is it that with the sine, they have both the sine and the cosine? Oh wait, never mind.
Yeah, with the one they're mixed together, with the two they're just separate.
Yeah.
Yeah, Michael?
Why are the
Um, it's it's a little hard to explain. It just that's the way it works out when you come up with the formulas. So yeah, it's there's not a simple way to say, well, it's because of this. All right, and our tangent formulas come from doing sine of u plus v over cosine of u plus v, or sine of u minus v over cosine of u minus v, and then simplifying, working with those to simplify them. So the tangent of u plus v is tangent u plus tangent v. So that looks pretty nice, but because tangent is a fraction, we have a fraction here, 1 minus tangent u tangent v. Now the tangent formulas are kind of nice because they're just tangents. Tangent of u minus v, tangent u minus tangent v. So that's pretty nice. But it's a fraction, 1 plus tangent u tangent v. So you can see that it's a lot of formulas, they're kind of similar, but the little bit of difference between them makes it is important. So that's part of the reason why I provide these. There's a lot there, a lot of details. And the tangent formulas, honestly you don't use those a lot. They don't come up a lot, and I never remember them. I have to really think about them to remember them. I have some other ways to remember the sines and cosines, but they don't have to do with stuff that we've learned yet. All right, so what I want to do is just go through some examples of the kinds of problems that we might see using these things. In the future, you'll see other kinds of problems to use these formulas, these identities, but we'll go through some things that kinds of problems that we'll see. All right, so we good? Any questions? Okay. And what I do with these, I have a list of them, and I just during the test I just write them all on the board, so they'll all be on the board up front. All right. So let's find the exact value. And just like usual, exact value is, when we're talking trigonometry, that's a hint that the problem is going to have something to do with the unit circle of sine of 15 degrees. So 15 degrees, not a nice unit circle angle. What this problem is asking us is to find the exact value, is a hint that it has to do with the unit circle. Find two unit circle values, or angles, sorry, that add or subtract to 15 degrees. And then we're going to use our formula for sine of u plus or minus v. And we'll separate that into sines and cosines of unit circle angles. So what are two nice unit circle angles that add or subtract to give us 15 degrees? 45 and 30. So we're saying that 15 degrees is 45 degrees minus 30 degrees. There are other pairs that will work. I usually try to think of the smallest ones first. So what we're doing is we want to find the sine of 45 degrees minus 30 degrees. And in my formula, my equation, my identity, that's going to be u, and that's going to be v. And then we're going to plug those in. So this is going to equal the sine of 45 cosine 30 minus cosine 45 sine 30. And now we have a nice unit circle problem. So what is the sine of 45 degrees? Square root of 2 over 2. Cosine of 30? One half. Square root of 3. Square root of 3 over 2. Minus cosine of 45? Square root of 2 over 2. Sine of 30? 1 half. All right, and then we can simplify this. We can multiply inside the square root. So we get square root of 6 over 4 minus square root of 2 over 4. And we cannot add or subtract inside the square root. So this is just going to be square root of 6 minus square root of 2 over 4. And that would be the exact value of the sine of 15 degrees. And sometimes if you search online for unit circles, you'll see unit circles where they have these other various angles that are sums or differences of the unit circle angles that we've done, and they have the coordinates, the x and the y coordinates all look like those things. So we could kind of have more unit circle angles, nice unit circle angles, than we've actually talked about. Gets kind of messy with these kinds of things, but you could do it. All right, questions there? All right, let's look at one that's a little more interesting. We want to find the exact value of the cosine of 7 pi over 12. So now we're working in radians, but again, what we want to do, find unit circle angles. That add or subtract to give 7 pi over 12. And then we're going to use the cosine of u plus or minus v, depending on what angles we find. All right. So for this one, part of the challenge is just really the challenge is figuring out how we're going to split up 7 pi over 12. So what are our denominators for our unit circle angles? 3, 4, and 6 are denominators. 2, 3, 4, or 2. So can we combine 3 and 4 in a nice way to give us 7? And get a common denominator of 12? How about pi over 3 plus pi over 4? So when I find my common denominator, I'm going to multiply pi over 3 by 4 over 4, pi over 4 by 3 over 3. So in the top I get 3 plus 4, and then the bottom I get 3 times 4. So then we say that we want to find the cosine of pi over 3 plus pi over 4. And so we say that's going to be, this is in my formula, that's my u, and that's my v. So this is the cosine of pi over 3 cosine pi over 4 minus sine pi over 3 sine pi over 4. And now we have a unit circle problem. Cosine pi over 3, 1 half. Cosine pi over 4, square root 2 over 2, minus sine pi over 3, square root of 3 over 2, sine pi over 4, square root of 2 over 2. So I get the square root of 2 over 4 minus the square root of 6 over 4. So square root of 2 minus square root of 6 over 4. And that combination of square root of 2 and square root of 6 shows up a lot for these kinds of problems that we end up doing, because our unit circle, our coordinates on the unit circle are square root of 3 and square root of 2. We end up with those combinations a lot. All right, questions on that example? All right, let's look at one where we kind of have to go the other direction. We want to find the exact value so we're not just plugging this into our calculator of the cosine of 78, cosine 18, plus the sine of 78, sine of 18. So for this one, what the problem is asking us to do is recognize the form. So we want to match this up when you see these, and this is where this would come up, maybe not in a contrived example like this where we have nice unit circle angles, but sometimes in calculation you get combinations of things like this, and we see these cosines together and these sines together, and we say, well, that kind of looks like one of those sum or difference formulas, and then we want to use them to combine that into a simpler thing. So which formula does this look like? Cosine of u minus v, right? Because we have the plus sign there, we have the cosines together, the sines together. So this, in our formula, this is u, and that's v. So we have the cosine. We want to find the cosine of 78 minus 18, which is cosine of 60. And now we have a nice unit circle angle, cosine of 60 degrees, 1/2. Now if you had variables here, x's and y's, something, you could combine this messy thing into cosine of x minus y, for example. And that might be easier to work with. It might be desirable to work with it that way. All right, we good there? So we're going, let me back up here. So we're going from this to this. So all of this turns into that.
Okay.
Does that make sense? So we took all of this and put it into that.
Yeah.
Okay, good. All right, the other nice thing about these formulas is they give us the opportunity, the ability to verify new kinds of identities. And I know we've all been thinking, I would really like to verify new kinds of identities, because the kinds of identities we have been verifying are getting mundane. So let's verify one of our favorite kinds of identities. Our cofunction identity, that sine of 90 degrees minus x equals cosine x. Does look familiar to something that maybe half of you saw a few days ago? Yeah? 90 degrees might have been written as pi over 2. So I told you we talked about this identity before, and when we talked about it before, we talked about it in terms of complementary angles in the right triangle, and how the the opposite and the adjacent sides switch around for the two complementary angles? Well, now we're going to use identities, formulas, to identify this, or to verify this. So this is going to be my u, and this is my v. And we're going to use the sign of u minus v. So I'm going to rewrite this as the sine of 90 cosine of x minus cosine 90 sine x. Well, what's the sine of 90? 1. What is the cosine of 90? 0. And we verified our cofunction identity using our sign difference formula. And it's always exciting in math when we can get to the same place from two different ways. So before we talked about complementary angles in our right triangle, here we're using difference formulas and identities. All right, the other nice thing about these formulas is they give us the opportunity to solve new kinds of equations. Because just like with the identities, we thought these equations that we've been solving, they all seem the same now. Let's have a new challenge. So let's solve the cosine of x plus pi over 4 minus the cosine of x minus pi over 4 equals 1. So we'll solve that equation. Well, we have two sets here, u and v there, and u and v there. So we're going to use two formulas, a sum formula and a difference formula. So I'm going to plug these into my cosine of u plus v. So we have the cosine of x cosine pi over 4 minus sine x sine pi over 4. I'm going to say minus, and then I'm going to put a set of parentheses because we're subtracting the entire quantity. Cosine x sine pi over 4 plus, whoops, should be a cosine, plus sine x sine pi over 4, and all that equals 1. Well, this is really nice because look what happens. We have a cosine x cosine pi over 4 minus cosine x cosine pi over 4. Those go away. We have a minus sine x sine pi over 4 minus sine x sine pi over 4. So we get minus 2 sine x sine pi over 4 equals 1. We can divide by negative 2 here. Equals negative 1/2. And what's the sine of pi over 4? Square root of 2 over 2. So I can say square root of 2 over 2 sine x, these are multiplying, equals minus 1/2. Multiply by 2, divide by the square root of 2. I get the sine x equals negative 1 over the square root of 2, which is the same as negative square root 2 over 2. And now we're back to the kind of equation that we've looked at before. Now we're looking at the unit circle, and we say, where does sine x equal negative square root of 2 over 2? X equals (5 pi over 4) plus 2n pi. And what's our other one? 7 pi over 4 plus 2n pi. And there's the solution to this equation that might have looked a little intimidating at first, but it really wasn't bad. All right, questions? Okay, last example. My favorite example of this entire second part of chapter 5. I love this example. And someone in the 6th period class guessed what this example had to do with, because she said all my favorite examples have to do with this concept. We want to find the exact value of cosine of u minus v if sine u is 5/13, cosine v is negative 3/5, and u and v are in quadrant 2. All right, anybody want to guess what this example has to do with? Triangles, yes. It's my favorite kind of example with trigonometry, is when we actually get to use triangles. All right, so we want cosine u minus v. So we know that cosine of u minus v from our formula, cosine u cosine v plus sine u sine v. Well, what are we missing? We have sine u and we have cosine v. What do we need? We need cosine u and sine v. How are we going to get those?
Make them up.
Make them up? We get to use 2 triangles. We get to use a triangle for u. So our u triangle. And I'm going to draw, we're in quadrant 2, so I'm going to draw my triangle this way. There's u. Sine u is 5/13. So what is this missing side? Pythagorean triple? 12, and since we're in the second quadrant, negative 12. So let's see, we need cosine u is negative 12/13. Negative because we're in the second quadrant, that's good. And then our v triangle. We're in the second quadrant, so there's my v triangle. And it says the cosine of v is negative 3/5. This side? 4. And we get the sine of v is 4/5. So now we plug all of this stuff into our formula. Cosine of u minus v is cosine u, negative 12/13, cosine v, negative 3/5. And we're adding plus sine u, 5/13, times sine v, 4/5. And then we multiply this out. 65ths plus 20 65ths equals 56 65ths. That's a nice answer, isn't it? And then we can cancel out the 5 and cancel out the 6, and it just equals 1, right? All right. Right. Questions? It's really nice when we can, and you will have the opportunity on a couple of homework problems to draw some triangles. One thing about the homework, when you do problems that involve the tangent of u plus v, tangent u minus v, you'll get answers that look like tangent u minus v is something like 1 plus the square root of 3 over 1 minus the square root of 3. In the book, they do lots of stuff to rationalize the denominator. Leave it written like that. This is fine. This shows me that you understand how to apply the formula. There's too many ways to make arithmetic errors between this and the actual rationalized answer to make it even worth doing. So just leave it written like, leave your tangent answers written like this. All right. All right, there we go.